Okay, good afternoon. Today we will continue our discussion still about the fluid flow, and we will discuss about the application of still the ideal Bernoulli. So hopefully today we can finish this part of the chapter. Okay, last time we already discussed about the pipe fitting. The pipe fitting is tools or device that used to connect different size of pipe. For example, that's one purpose of pipe fitting. And from the example, we use two types of pipe fitting, which is diffuser and also reducer. Both are connecting two different size of pipe. Diffuser is connecting smaller to larger, and reducer is vice versa. And basically, using the principle of mass balance. So this is the mass balance, and then energy balance. You can derive the equation to correlate first from mass balance. You can correlate the velocity as a function of the area. And then you find out that if you have diffuser, which have a larger diameter at the outlet, so you will have smaller velocity at the outlet and higher pressure at the outlet. Inverse, for reducer, then you will have smaller diameters at the outlet, and then higher velocity, and then smaller pressure. The same principle is applying the mass balance and energy balance, Bernoulli ideal. And the other types of pipe fitting is called sudden enlargement. Basically, sudden enlargement is similar with a diffuser. So it's connected smaller diameter to the larger diameter of pipe. But the difference is in sudden enlargement, the change in diameter is sudden. Let's call it sudden. Yeah. If for the diffuser, the change in diameter is gradually increased, but for the sudden enlargement is not gradual. So if you take account position 1, actually you can also take position 1 here, position 2 here, inlet and outlet. If you compare at position number 1 and position number 2, basically how to derive the mass balance and the Bernoulli equation is exactly the same, because mass balance and energy balance is only comparing two different points. So we do not see how the fluid will flow throughout the fitting. But you only compare at the inlet point or at the small diameters and bigger diameters. So if you compare point 1 and point 2, small diameters and bigger diameters, first, if you take the baseline at the middle, then the position of point 1 and point 2 are the same. So the potential energy is the same at point 1 and point 2. So the derivation of the mass balance, you can get this correlation as well. You can correlate the velocity at the outlet as the function of velocity of the inlet by comparing the area or the diameters. And then since at the sudden enlargement, the inlet diameter compared to the outlet is lower, then you will have lower velocity at the outlet. Because you have higher diameter at the outlet, then the velocity become lower, and also the pressure become higher. For sudden enlargement, the equation will be exactly as the same as diffusion. The equation. But if you compare the flow pattern, what will be the difference between diffuser? If you see the construction of diffuser is like this one, and then the fluid is flowing inside the diffuser, comparing if the fluid is flowing inside the sudden enlargement. What will be the differences in flow pattern?
Sir, so Z will be the same, right, sir? Even for the diffuser, right?
Yes, yes, because you take the baseline at the middle, at the midpoint of the circle. So it's the
Okay.
one. So the equation is exactly the same. How you correlate the velocity and how you correlate the pressure will be exactly the same between sudden enlargement and diffuser. But the differences actually are in the flow pattern. Because in sudden enlargement, for example, like this one, right? The fluid is flowing smoothly, but here there will be some turbulence around the enlargement area. Comparing if you are flowing the fluid in here, so the flow will be like this one, right? This is the flow pattern. But for this one, it become like this one, and then this one. For example, like this one. Because it has some point where the area is suddenly changed. And what will be the effect of the flow pattern? Actually, if you only see from the Bernoulli ideal, you will get exactly the same equation, right? This is velocity at outlet as the function of pressure difference. It should be exactly the same as which one? If you derive, okay, if you okay, if you derive the equation to correlate velocity at point 2 from this one, so you change, actually you need to change velocity at point 1 as a function of point 2. So it's like in the inverse equation, but should be no problem. Then you will have the same equation like this one. Actually, if you derive the equation for the diffuser, you will have exactly this equation. But actually, in the real case, because Bernoulli ideal doesn't, or it's assuming that there will be no energy loss, right? But in the real case, this turbulence around the enlargement area will cause some energy loss. So what will be the effect in sudden enlargement? The velocity at point 2 will be lower than velocity at point 2 at the diffuser. This is due to this one. But now we only consider the ideal Bernoulli. So we assume that velocity at point 2 for diffuser and sudden enlargement is the same, as long as the diameter ratio or the size of the diameter inlet and outlet are also the same. How to correlate the flow pattern into the ideal into the non-ideal calculation? Actually, we use, this is the fitting constant. So this one, the value is between 0 and 1. This one, the constant is maximum is 1. It means when the constant is 1, then the flow is considered ideal, become above equation. This one, the constant is, the value is 1, right? That will be the effect. Any question first? You can get this equation as well for the diffuser by deriving this one. But this one as U1, but this one as U at point 2. So should be no problem, right? You just change the notation from 1 into 2, and then you correlate from this one.
So, sir, U2 is already a combination of U in point 2 minus U at point 1, is it?
Sorry?
U2 here is
Mhm.
already a combination of the kinetic energy at point 2 minus point 1, is it?
No, U2 is velocity at point 2.
Okay,
This one is
yes.
velocity at point 1. So you have velocity, you will have pressure, and you will have potential, right? This one also have this one. But this one and this one, Z1 and Z2 are the same. So you only consider the pressure and the velocity.
Tapi U2 is already udah kayak disambungin gitu ya, sir. Udah dijadiin satu unit gitu.
Oh, U2, what do you mean?
U2 is equal to U at point 2 minus U at point 1, sir. Is that right?
No, U2 is just the velocity. So you get from this one, but it's at point. Actually, you can rederive the equation by I think the full equation is here, right? So the general equation is this one, and then you can get U2 square equals which one, right? From this one, you can do the the move of the parameters, right? So you take all the parameters beside U2 to the left or to the right, and then you change U1 as the function of U2 using this equation.
Iya, ngerti, sir. Oke,
Yeah.
I got it,
So
sir.
it's the value of U2, not U1 minus U2. So this is the value of U2. The value,
Oh, oke. Since you udah diganti ya, sir.
yes, it's already replaced the by using the ratio of velocity. You can try later. Please try rederive. You do the same exactly calculation like the diffuser, but calculate as U2. This one as U1, right? Or actually you can rewrite this equation and then put U1 at the left side and put all the parameters at the right side. And then you get U1 as akar something, right? Root of something. And then U1 you replace with U2 by using this one. Then you will have this one. Okay. Okay, any other question? Okay, if there is no question, same for the sudden contraction. It will be exactly the same as reducer, but you will have sudden change in diameter in one part of the sudden contraction. So at this area, the change in diameter is sudden. So if with the same derivation, the same mass balance and energy balance, then you will have U2 as well. Actually, the equation, wait. Okay, don't be confused because sometimes delta is P2 minus P1, sometimes P1 minus P2, and the ratio is D1 per D2 or sometimes D2 per D1. Just please check again the from initial equation and then try to rederive.
Sir, what's important is final minus initial, right? Or final over initial.
Which one? Which one?
Like for example, P1 and P2. What's important is, wait,
Yeah,
tarik
because
ketuker.
I think in this slide there the parameters is changed because the other like this one, right? You can see this one P2 minus P1 and then this one D1 minus D2, right? But at this one is P1 minus P2, but at the denominator is D2 minus D1. So just changing the side of the equation. But no need to memorize this one. So I ask you, please do not directly memorize the equation, but please understand that these equations comes from the Bernoulli equation with assumption the same z. Okay, I'll clear this up. Okay, so basically you will have mass balance equation, and then you will have this correlation, and then you have Bernoulli equation, and then with the same z, then you will have this one. Then you can memindah-mindah parameter. You can calculate like P2 minus P1 equals what? P1 minus P2 equals something. And then U2 equals what? And then yeah, equals. Please try to rederive this equation. Ya, jadi jangan dihafal apa istilahnya, jangan dihafal mati lah gitu ya. Please do not just remember, please do not remember just the final formula, but you need to understand from where the formula comes from. Okay? As the same as the sudden enlargement, the sudden contraction will also have some constant. The value is also from 0 to 1. The further from 1, it means it's more non-ideal. The closer to 1, it means closer to ideal.
Sir, kalau misalnya the constant itu biasa dapatnya dari mana? So kayak U2 itu ada kayak there's an ideal U2, terus kayak you have to find the constant inside or something, sir? I don't get it, sir.
Okay, basically there is two ways to calculate the constant. First, if you have actually it comes from the experiment. Like if you have sudden enlargement or sudden contraction, you will have the value of U1, right? Experimentally, you find the value of U1. And then by calculating the mass balance, and then you will have the theoretical value of U2. Okay, or you just need to calculate just one real value of velocity, either at point 1 or either at point 2. And then what you do in the experiment is also you calculate the pressure difference. How to calculate the pressure difference between 2 points? You place some device to calculate the pressure difference. Actually, we will discuss. You still remember manometers, right? This one, the
Yes, sir.
U-shaped tube. Then you place U-shaped tube in this part and this part. Then you calculate the pressure difference. Pressure difference is actually calculating this one, right? And then you make some correlation. If you vary the velocity, or for example, you calculate or not calculate, you measure the velocity at point 2 by using the flow meters. And then you calculate the pressure difference. Then you will have some, this value is constant, right? The density, the diameter is always constant. So the one that you vary is velocity at point 2. Then from the variation of velocity at point 2, you will have the value of delta P, the pressure difference. Then you make a curve, right? So from the curve, you can get the gradient, and then you can get the constant. And this constant is actually how to call it? The characteristic of the specific characteristic of the sudden contraction, or specific characteristic of the fitting. So the different fitting will have different value of constant. It will be depending on the ratio of the diameters. It will be depending of the roughness of inside of the fitting and something like that. And the constant value are calculated from experiment.
Okay, sir, it makes sense. It makes sense. Yeah.
Okay. But for the ideal equation, for the ideal condition, because you only analyze from point 1 and point 2, you do not consider the flow pattern. Ideal condition, just assume everything is always there, right? There is no energy loss, something like that. Then you use the first equation, assuming that the constant is always 1, the value. Okay. Now we go to the flow rate measurement device, and actually this device that we will discuss is used with the principle of the mass balance and Bernoulli equation. So first we call pitot tube. Pitot tube is used to measure the plane velocity. So this is the pitot tube. So if the direction of the plane is over there, and then the pitot tube, the tip of the tube will also points to the same direction as the plane. So it will have different direction with the fluid flow. So like this one. This is the plane direction will be this one, and this is the fluid direction, right? Okay, so this is the pitot tube, the smaller tube. Inside the pitot tube, this is, ini apa? Is the manometers. The small tubes that have U shape, and then inside the manometers, you will have, for example, this is air, right? The fluid here is air, but inside the manometers, you will have liquid, for example, with the density of rho A. So A is the liquid inside the manometers. So what happens when the plane are moving to the left and the air are moving to the right, then the air will goes into the pitot tube, pressing the liquid inside the manometers until some condition that the liquid are in static condition. That's why it's called the static tube. Okay, what will be happen, or how the pitot tube correlate the flow rate? First, it's comparing the pressure between point 1 and point 2. Point 1 is the point quite further from the pitot tube, representing the velocity of the air. Yeah, point 1 representing the velocity of air. The velocity of air will be the same as the velocity of plane, right? Because it's moving in the different direction only. Okay, point 1 is the velocity of air, and point 2 is the velocity of air exactly inside the mouth of the static tube or the pitot tube. What will be the velocity of point 2? Okay, or
Kok bisa gitu sih, sir?
yeah, that's the principle of the pitot tube. So I'll repeat that. The air some of the air will be flowing inside the pitot tube, right? Because it has the hole at the tube. Then the flow will be like this. It will be pressing the liquid, but the condition after pressing after some pressure are given, and then the liquid will be in the static position, showing the pressure difference between point 1 and point 2. Because it's here is also flowing air, right? Bener nggak?
Yes, sir.
Correct, right? So at here, you can consider that the velocity, yeah, the velocity will be the same as the velocity at point 1 because it's the velocity of air. But at point 2, which is exactly at the mouth of the pitot tube, what will be the velocity? Since its pressure, first it's moving, right? It's moving. The initial condition before the plane are moving, what will be the heat difference in the liquid in the manometers?
No difference.
No difference, correct. When the plane are in the is not moving yet, then there will be no difference in the liquid of the manometers. But when the plane are moving and air are moving in the opposite direction, then the air will be pressing the liquid inside the manometers until some pressure difference are achieved and the liquid are in static condition. So here is representing the velocity at point 1 because it's the same, right? And it will also representing the pressure at point 1 because all are connected to the open air, right? Okay, and then at point 2, it's already inside the mouth of the tube. But after pressing the liquid inside the manometers, all inside the pitot tube are in static condition. Ya, jadi kan at the first the air will flowing inside the pitot tube, pressing the manometers, and then the liquid inside manometers are showing heat difference, and then it's become static. After the liquid in the manometer becomes static, how about the air inside the tube?
Will it be the same as 2, sir?
Yeah, yeah. So all the air inside the tube will also in the static condition, right?
Yes, sir.
Yes, that's why the velocity at point 2 will become 0. So if you have Bernoulli, this one, right? This is the full Bernoulli equation. And then at point 1 and point 2, the position is the same. At point 2, the velocity is 0, right? So you can correlate the point 1, you can, after this one, you can take out this one, right? So it becomes Okay, then okay, yeah, correct, right? Then wait. P1, okay. Okay, so you will have this equation. This one, I don't know why there's a lot of typo in this slide. Sorry for that. Okay. Okay. So velocity at point one, which is the velocity of the air, which also the velocity of the plane, is you can calculate by this equation. The root of 2 times P2 minus P1 divided by rho. Okay. My question is how to calculate P2 minus P1? If you have this arrangement, how to calculate P2 minus P1? By calculating the heat difference, right? So P2 minus P1 will be, sorry, will be density of the fluid inside nanometers times H times delta H. This one, you incorporate it to this equation, or this equation. So by measuring the heat difference inside the manometers, you can calculate the pressure difference between point 1 and point 2. Which one is higher, pressure at point 2 or pressure at point 1? Of course, pressure at point 2, right? It's showing that the right leg is lower than the left leg. It means at point 2, the pressure is higher. So the delta between pressure at point 2 and point 1 can be calculated by using the hydrostatic equation. Please do not forget this equation. Rho times G times delta H. But the rho that used is the rho or the density inside the manometers. How about rho here?
Rho of the air, right, sir?
Yes, this is the density of the gas or air. Jadi jangan kebalik-balik ya. In the calculation of the velocity, because this is velocity is the flow rate, right? The how pitot tube can calculate the flow rate or the velocity is by using this phenomena, by applying the Bernoulli equation, and then you find out the correlation between the velocity of air as the function of the pressure difference. Pressure difference can be calculated by calculating the heat difference in the manometers by using the hydrostatic equation, rho G delta H. But the rho here is the rho of the liquid inside manometers. But to calculate the velocity, then you have to divide it by the rho of the air. Again, please do not, if you can remember, then it's very good. But if you forget, then you can do the derivation by assuming, but you already know the assumption of the pitot tube at point 2, the velocity will be 0. Okay, the arrangement of pitot tube, actually there's some arrangement, right? In here you can see the arrangement can be in the left figure or on the right figure. It's the same. But basically, it comparing the pressure and the velocity at point 1, which is the pressure and the velocity of air, right? Or the velocity of the plane. And then at point 2 is velocity inside the pipe, inside the tube, which is 0. Okay, any question?
Sir,
Yep.
Jadi ceritanya teh kayak air keeps on going in with an amount of pressure until the pressure inside the tube sama di luar teh sama gitu, sir.
Sorry again.
Ini ceritanya teh kayak the air kan
Mhm.
ini kan rushing to the tube, right?
Yes,
Jadi pressure yang di dalam tube-nya itu it will be equal to just at the tip, right, sir? Makanya U-nya zero kan because it's not
yes,
apa the air dari luar itu nggak bisa masuk gitu.
yes.
Cuman nyamain the pressure kan, sir?
Correct. Yes. So
Oke.
the air will be flowing inside, and then it will pressurize the liquid, right? But since liquid has a higher density, that at some point the liquid will stop moving. So it means the pressure is already balanced. Correct. So the pressure given by the air to the liquid is already balanced by the pressure given by the liquid. And also it will shows the pressure difference between the air inside the tube and between the air outside the tube. Oke, menjawab pertanyaan atau malah membingungkan?
Ngejawab, sir. It's okay. I understand now, sir.
Yeah, the concept is air first is still flowing inside the tube, but since there is liquid, right? If there is no liquid, then air uh, will comes out, right, from the other end of the tube. But since there is liquid inside the manometers, then the liquid will hold the pressure from the air, and then it will create pressure difference, and then the air inside the tube will stop moving. Okay.
Sir, kalau yang CP itu, is it the same kayak tadi the constant yang
Yes.
itu?
Correct. So CP is against some device will always have constant. It's actually basically is the correction factor from the ideal condition. So if the condition is ideal, then the constant is exactly 1. But if it's not, then it will be lower than 1. If it's very, very non-ideal, it will be getting smaller and smaller. The non-ideality comes from the flow pattern, basically. Comes from the flow pattern, and later it also comes from the friction between the fluid and the wall of the pipe. But we will discuss it later in the slide number 5. But since we still discussing about the Bernoulli ideal, which is not do not take account of the energy that lost, so the constant is 1 for now. Okay. Then we go to other types of flow measuring device. This is called orifice meter. So basically, if you see in the pipe, orifice is a plate that placed inside the pipe. Then you will have small aperture in the middle. So this one is the aperture. So what will happen if water, for example, are flowing inside the pipe? It will goes this one, right? And then it will goes like this. It will be the same as what? The phenomena here will be the same as sudden enlargement. And from the derivation of sudden enlargement equation, you will have correlation between the two as the function of 1, and then pressure will be higher, right? Sorry, pressure will be, if you have smaller diameters, I need to correct. If you have smaller diameters, then U2 will be higher or lower? Higher. and then the pressure will be lower, right? If you have this one, P2 is the orifice diameters. Okay, because we will have pressure difference, how to calculate the flow rate by using orifice. Basically, in the orifice, you just install the manometers here. And then you fill the manometers with some fluid, so it will show the height difference. The principle is the same as the pitot tube, but here you combine the principle of sudden, not sudden enlargement, sudden contraction, right? Sorry, this one. This one is the sudden contraction, so the diameter is reduced, and the pressure is increased. So the pressure here will be higher than pressure at point 1. And the same, you do the calculation by using the mass balance, combine it with the energy balance, then you can calculate the velocity. V2 is velocity at point 2. I'm sorry, the symbol is also changed. This is the velocity, linear velocity. And this one is volumetric velocity. This is meter per second. This is cubic meters per second. This one is meter per second. Okay, how about this one? Beta is basically this one. The smaller diameters divided by bigger diameters. So the equation should be exactly the same as the sudden contraction. And how about how to calculate P2 minus P1 or P1 minus, which one is higher? Oh, because P2 is lower, then the figure is, why nobody correct me? Salah gambarnya ya, sorry. Because P2 is lower than P1, then it should be like this. Okay, after you get the equation to calculate the velocity at point 2, if you want to calculate the volumetric velocity, then you multiply by the area. This is the area of orifice. The area of this one. This one, this. If there is, if you take account the non-ideal condition, then you just multiply by the constant. Okay, any question?
Sorry, sir. Beta is the small d over big D square, right?
Yep.
All right. Okay.
This one. The diameter ratio. Okay. Other types is called the Venturi. So basically, it's the same. It's same as a reducer, right? So reducer, by decreasing the diameters, because D1 is higher than D2, then at point 2, same as the orifice, the velocity will be increased, and then the pressure will be decreased. Same, because the diameter is smaller. So smaller diameters will result in higher velocity and smaller pressure. Then you do the mass balance. This is from mass balance. This is from Bernoulli. Basically you will have same equation. Just in this slide, actually this slide try to challenge you if you change the parameters, like sometimes it's on the left, sometimes on the right, and sometimes it's in the nominators, sometimes in the denominators. Okay, so this one basically you will have the same equation like this one, right? So from this one, V2 is this one, P1 minus P2, blah blah blah, and this one is this one. If you put this into the uh, to the right side, it should be the same. You can check it later. So if the ideal, this is the ideal, the constant is 1. If the non-ideal, then you need to know the value of the constants. Against, if it's ideal, the constant is 1. Okay, but sometimes it's just for the additional information. If or you already know the velocity, this is the velocity, linear velocity. If you want to calculate the flow rate is cubic meters per second, then you just need to multiply it by the area, cross area.
Area and density, right, sir?
Sorry, if just should be just only area. If the flow rate, you change from the linear velocity, meter per second, change into the volumetric flow rate, cubic meters per second, then you just multiply by the area. No need to
Okay,
multiply
okay,
by.
sir. Yeah. Okay.
If you want to calculate the mass flow rate, then you need to calculate mass flow rate is kilogram per second, right? So you need to multiply it by the density. So this one, yeah, I need to do some correction. The root should be until this one only. Because you want to multiply by the, this is the area. This is the constant, right? Same. Then you multiply by the density of the fluid. What is y? Actually, for the ideal, again, you do not need to consider y, but if you do some real calculation, actually for the venturi or the orifice, you need this kind of the graph. Y is the expansion factor. So you need to correlate between the pressure P2 per P1 and then the ratio of the diameters, beta. This one is actually beta. And then you take account these two parameters, and then you use this graph to calculate expansion factor. How to calculate? First, you need to calculate P2 minus, P2 over P1. And then you need to see from your system what is the ratio between the smaller divided by the higher diameters. Then you just use it. For example, if the pressure ratio is 0.8, and then this one, and then if the orifice divided by the higher diameters is 1, and then you just take, then you take the last one, then you get the value.
Sir, question, sir.
Yep.
Is this the expansion factor of the width of the difference in diameter, or the expansion factor of the liquid, sir?
Sorry.
Is this the expansion factor of the diameter? For example, venturi meter, the difference in the gap of the hole, or something, sir?
Oh,
What's the
what's
expansion,
the
sir?
meaning, right? Okay. Basically, this one is normally used to calculate if you have venturimeters to calculate the velocity of gas. Okay, and then because what happened in gas, if you flow into this kind of arrangement, the pressure will change, right? If the pressure is changed, gas will have some differences in density. Still remember, right? Because gas is considered compressible. So if there is some change in the pressure, the density will change. So actually, this Y is calling expansion factor because when flowing into the venturi or in the orifice, because it's like compression, like compressed, and then the pressure is not compressed. Basically, term-wise is not compressed because P2 is the diameter at point 2 is smaller, then the pressure will be lower, right? This one. So the gas will have expansion because it comes from the bigger pressure to the lower pressure. It's called expansion. Balikannya,
Okay.
the inverse is compression. Compression if the gas comes from lower pressure to higher pressure. But this one is expansion. So in expansion, since there's some pressure difference, the density is different, and actually the expansion factor are calculated to compensate the change in the density due to the expansion. So it is used to calculate mass flow rate. This is mass flow rate. Don't forget to correct this one, right? Tanda akarnya tidak sampai ke densitas. Because volumetric flow rate is flow rate times A. Mass flow rate is volumetric flow rate times rho, or this one. So the density should be not under the root equation.
Okay, sir.
Okay. Should we continue or should we break for tomorrow?
Maybe we should break, sir. We just had 2 quizzes before this, sir, like consecutively, sir.
Okay, then I will stop the lecture until this part. So tomorrow we will finish this part of the lecture. Okay, or do you still have any question regarding today's lecture? Okay, if you have no question,
Sir,
yes.
maybe not about this lecture in particular, but I've been noticing that the lectures that we had was recorded, but I can't seem to find where
In the
is the
YouTube
recordings. Oh,
or
so it's actually uploaded in YouTube. Is
yep,
that
yep.
so?
You can find the link also if you go to the Google Classroom. I have link the YouTube into the Google Classroom. You just go to the lecture recorded video.
All right, sir. I'm just trying to make sure. Thank you so much.
But please check whether I have already uploaded all the video because maybe last time I also forgot. So please remind me if there is some part of the lecture that I have not been uploaded.
All right, sir. Thank you.
Okay. Any other question? Okay. If there is no more question, then I'll stop the lecture for now. Then we will discuss for tomorrow. Okay. Thank you. Good afternoon.